Hello students, welcome to another video of calculus. Today we will discuss the monotone sequence and one theorem, that is monotone convergence theorem. So first of all we will write our title and monotone sequence. Monotone sequence. So before the starting of monotone sequence, definition of monotone sequence, we will see the definitions of increasing and decreasing sequence. So the first definition is decreasing sequence. First definition we will take as increasing sequence. So let x is equals to xn, this is the notation of sequence, be a sequence of real numbers, be a sequence of real numbers, be sequence of real numbers. Then we say that the sequence is increasing. We say that the sequence xn is increasing. Sequence xn is increasing if it satisfies the inequality. If it satisfies the inequality, inequality means if the first element of that sequence is either less than or equals to the second element of that sequence is again less than or equals to the third element, another next element is again less equal the first elements, and so on. That is, suppose the nth element of the sequence is less than or equals to n plus 1th element, then that is all the elements of the sequence, second element is greater than or equals to first element, third element is greater than or equals to second element, that is x1, first element is less than or equals to second is less than or equals to third, and so on. Then that sequence is called increasing, that is the numbers are increasing, that is the sequence. Then we say that the sequence is increasing if the elements of sequence are in increasing order, that is first element is less than or equals to second is less equal third is less equal fourth, and so on. Then we say that this sequence is increasing sequence. First, for example, if we take, suppose the sequence xn is equals to suppose n, then 1 is less equal to, then the elements of this sequence are, first element is 1, second is 2, third is 3, 4, and so on. This is the, here first element is less equal, second is less equal, third is less equal, and so on. Nth element is n, and next is n plus 1, and so on. Here nth element will be n, next one is n plus 1, all these natural numbers. So clearly this n is less equal n plus 1, and so on. So this sequence xn is equals to n is increasing sequence. Now the second definition is decreasing sequence. Second definition is decreasing. We say that the sequence xn is decreasing. We say that sequence xn is decreasing. Sequence xn is decreasing again if it satisfies the inequality, if it satisfies the inequality, x1 is greater equal x2 is greater equal x3, and so on. That is nth term is greater equal n plus 1th term. This is xn plus 1, and so on. This sequence is called decreasing sequence, that is the first term is the greater among the remaining terms. For if we take, suppose for example, if we take xn is equals to minus of n, then we get minus 1, first element is minus 1, second is minus 2, third is minus 3, and so on. So the nth element is minus n, next element is minus n plus 1, and so on. So this minus 1 is greater than or equals to 2, sorry, minus 2 is greater equal, minus 3 is greater equal, all the terms. So this sequence is a decreasing sequence. Now we will come on the main topic, which is monotone sequence. So third definition is monotone sequence. Sequence xn is said to be monotone if it is either increasing or decreasing. Sequence xn is said to be monotone sequence if it is either increasing or decreasing. If the sequence is increasing, then we say that the sequence is monotone sequence. If the sequence is decreasing, then also we say that given sequence is monotone sequence. We say that the sequence xn is monotone. We say that the sequence xn is monotone sequence if it is either increasing or decreasing. If it is either increasing or decreasing. It is either increasing or decreasing. Sequence xn is said to be monotone if it is either increasing sequence or decreasing sequence. So here the sequence n is increasing sequence, so this sequence xn is equals to is also monotone sequence. Second sequence xn is equals to minus n, this sequence is decreasing sequence, so this sequence xn is equals to minus n is also monotone sequence. Now we will see one theorem on this, which is monotone convergence theorem. Next topic is monotone convergence theorem. Monotone convergence theorem. This is important theorem, monotone convergence theorem. The statement of this theorem is a monotone sequence of real numbers a monotone sequence of real numbers is convergent. A monotone sequence of real number is convergent if and only if it is bounded. If and only if it is bounded. Further is a subpart of this theorem is if that sequence x is equals to xn is sequence, if the sequence xn is a bounded increasing sequence, is a bounded increasing sequence, if the sequence is bounded increasing sequence, then that is the bounded increasing means increasing sequence which is bounded. If this sequence is increasing and bounded, then this sequence is converges to its supremum. Then limit n tends to infinity xn, limit of that sequence xn is equals to supremum of that sequence xn, such that n belongs to set of natural numbers. Supremum, we have seen the definition of supremum and infimum in the first chapter. So here, if the sequence is bounded and increasing sequence, then the limit n tends to infinity xn, that is the limit of sequence is supremum whenever the sequence is bounded. The statement says that if the monotone sequence which is bounded, a monotone sequence which is convergent if and only if a monotone sequence of real numbers is convergent if and only if it is bounded, and if the sequence is bounded increasing, then that sequence converges to supremum. Also, if that sequence is bounded decreasing, then that sequence converges to infimum. So B part of the statement is if suppose y is equals to yn is a bounded sequence, is a bounded sequence a bounded sequence, then limit of that sequence xn, limit n tends to infinity, xn is equals to infimum of xn, such that n belongs to set of natural number, infimum of that sequence. So the statement of the given theorem is a monotone sequence of real numbers is convergent if and only if it is bounded. So in the first part we have to prove, that is, if you take the sequence is convergent, then we have to prove that it is bounded. And in the second part, if you we have to suppose that this sequence is bounded. There are two cases whenever the sequence is bounded. If the sequence is bounded and increasing sequence, then we have to prove that limit, that is the sequence converges to its supremum. And in the second part, if you take this converse part, that is sequence is bounded, and there are two possibilities. First possibility is bounded increasing, second possibility is bounded decreasing sequence. It is bounded decreasing sequence, bounded decreasing, then that sequence converges to its infimum. So we will see the proof. The first part of the theorem is obvious, that is, if you take a monotone sequence of real number which is convergent, then that sequence is obviously bounded. We have seen the result in the previous video, that I think in the last second video we have seen that every convergent sequence is bounded. Every convergent sequence is bounded. So first part is obvious. If you take monotone sequence of real number is convergent, then that sequence will be bounded by using that result. The result is every convergent sequence is bounded. Now in the converse part, if you take the sequence is bounded, then there are two cases. First case is bounded increasing sequence, then we have to prove that sequence converges to its supremum. And the second part is, if that yn sequence yn is bounded decreasing, then we have to prove that that sequence converges to its infimum. Now the first part is obvious. So in the proof, first of all we will write we will take the sequence as convergent sequence. So also we know that every convergent sequence is bounded. So as we know that every convergent sequence is bounded. Every convergent sequence is bounded. Every convergent sequence is bounded. Therefore here monotone sequence of real number, if the monotone sequence of real number is convergent, then that sequence will be bounded. Therefore a monotone sequence of real numbers, monotone sequence of real numbers is convergent, which is convergent. Monotone sequence of real number which is convergent, then that sequence will be bounded, then that xn will be bounded. Hence the first part is proved. Monotone sequence of real number, if that sequence is convergent, then that sequence is bounded by using this result. Now conversely we will suppose the sequence xn is bounded. Now conversely, if that x is equals to xn is bounded sequence, is bounded monotone sequence, bounded monotone sequence, bounded monotone sequence, then bounded monotone means either increasing or decreasing. So here bounded monotone means that sequence is bounded, but that sequence will be either increasing or decreasing. Therefore x is equals to xn, which is bounded, is either increasing or decreasing, increasing or decreasing, increasing or decreasing. Since that x is equals to xn is bounded and increasing or decreasing. If we take that sequence xn is increasing sequence. So first, for in the further statement we have seen the first case. So we will prove, first of all we will prove that case which is x is bounded and increasing. So let, or first we prove the sequence xn is bounded and increasing. First we prove the result for x is equals to xn is bounded and increasing. Bounded and increasing, since this sequence is bounded as well as increasing sequence, since x is equals to xn is bounded. So as the sequence is bounded, we can use the definition of bounded sequence. So therefore there exists some m belongs to set of natural numbers, there exists some m belongs to set of real numbers such that mod of xn is less than or equals to m. That is all the sequence. If we take the modulus of all these elements of xn, then that will be less equal m for all n belongs to natural numbers, means every element of that sequence is either less than or equals to, modulus of every element of the sequence is either less than or equals to m. Now we know that this mod xn is less equal m means this sequence is bounded, and also we know that a bounded sequence which is increasing. So by using completeness property we can write this sequence as supremum. Every bounded sequence which is increasing, that sequence has supremum. Therefore that was our completeness property. Therefore by completeness property, we can write this sequence has supremum, that is there exists some real number u such that u is supremum of all the xn, that is n belongs to set of natural. Supremum means least upper bound, least among all the upper bounds. So u is supremum of this sequence. Mod of xn is less equal m means sequence is bounded, also sequence is increasing sequence which this bounded means bounded above, increasing sequence which is bounded above has supremum. So there exists some u such that u is supremum of that sequence. Now we have to prove that our claim is this limit of this sequence is equals to supremum of xn. Here we have taken supremum is equals to u, then our claim is limit n tends to infinity xn is equals to the supremum means u. We have to prove this is our claim. So limit of that sequence exists means for all epsilon positive there exists some n belongs to natural number such that mod of xn minus that l, here u we have to prove that u. So mod of xn minus u must be less equal must be strictly less than epsilon for all n greater or equal n. So if we take any epsilon positive, if given epsilon is given, then as u is supremum, that is u is least upper bound. So there may be u is supremum means u is least upper bound, means least among all the upper bounds. So there does not exist any upper bound which is less than u. U is least upper bound, least among all the upper bounds. So there does not exist any upper bound which is less than u. So u is least among all the upper bounds. So for given epsilon positive, then we can write there does not exist any, suppose u minus epsilon. So this u minus epsilon is not an upper bound because u is least upper bound, is not an upper bound, not an upper bound of this set xn such that n belongs to natural number, of the set xn such that n belongs to set of natural numbers. Now hence we can write, hence there exists some xk, such that xk is in between, that is the xk is greater than this u minus epsilon, that xk is greater than u minus epsilon. There exists xk such that there exists some xk such that this xk is greater than u minus epsilon, because u minus epsilon is not an upper bound. So there may be some element of that sequence which is greater than this u minus epsilon, that is u minus epsilon is less than xk. There exists some xk such that this u minus epsilon is less than xk. In fact, we can write the sequence xn is increasing sequence. Sequence xn is increasing sequence, so there may be more than one element. So in fact, we can write as sequence xn is increasing, there is some xk which is greater than u minus epsilon, means all the elements greater than, that is elements after xk, that is xk plus 1, xk plus 2 and so on, all the elements are greater than this u minus epsilon. So we can write as the sequence is increasing, as the sequence is increasing, this implies xk is less than or equals to xn, that is elements xk plus 1, xk plus 2, xk plus 3 are greater than this xk, that is xk is less equal xk plus 1 is less equal xk plus 2. So we can write xk is less equal xn whenever n greater equal k, that is for the larger numbers k plus 1, k plus 2, then xk is less equal, sorry, xk is less equal xn. Now we can write this u minus epsilon is less than xk, xk is less equal n xn, xk is less equal xn, and this all the terms of the sequence are less than or equals to u, since u is supremum, because u is least among all the upper bounds. This is by definition of bounded sequence, and here we can write u is supremum, means all the terms of that sequence are either less than or equals to u, because by definition of sequence. So here we get u minus epsilon is less than xk, xk is less equal xn, xn is less than or equals to u. So we can write, just combining these equations, we can write u minus epsilon is strictly less than xk, then xk is less than or equals to xn, xn is less equal u, because u is supremum, and u is clearly less than u plus epsilon. We are adding some number to u, so u is clearly less than u plus epsilon. So here we can just write it as this u minus epsilon is less than or equals to xn is less than or equals to u plus epsilon. So if we subtract u from all the sides, we can get minus epsilon is less equal xn minus u is less than or equals to, sorry, instead of less than or equals to, we have to write strictly less than, because this u minus epsilon is strictly less than xn. So here write strictly less than, again this is again strictly less than. So this minus epsilon is less than xn, minus u is less than epsilon. So this is by using the result of absolute value, that is mod a is less equal c if and only if minus c is less equal less equal, sorry, using that result mod a less equal c less if and only if minus c less equal a less equal a less equal c, we can write here mod of xn minus u is strictly less than epsilon by using property minus mod of a less equal c if and only if minus c less equal a less equal c. Using this property we can write this. So this is for, as we have taken this for all n greater equal k, because here we have seen that this xk is less equal xn for all n greater equal k. So using that result here we can write this is for all n greater equal k. This is the definition of limit. So this implies limit of sequence xn is u, limit n tends to infinity xn is equals to u, that is the limit of the sequence xn is supremum of xn such that n belongs to set of natural numbers. Hence the proof of first part. The proof of second part we will see in the next video.